Hey, welcome back. Today I have a little tooling modification here. Not overly exciting, but we are dealing with a hardened tool holder, so I figured this might be interesting how to approach something like this. And not everything did go as I tended to. This was quite chaotic, to be honest, but the end result is what I intended. And also we're going to play with the hardness tester and look at several items and materials in the shop and compare their hardness and kind of try to qualify hardness in some way. So let's have a go. So if you remember, a few months back, well, November 2023, I made this low-profile dial test indicator holder, and it has proven to work very, very well. There is not much I would change on it. When I finished it, I put it in this weld-on holder here, and all these HSK, that's the interface down here, tool holders have in common that they are fairly long. Even the shortest ER11 tool holders that I have are still sticking out fairly long. So I figured it would be nice if this holder was short. Take this. Yeah, I could lap the shaft of this indicator holder a tiny bit smaller because it's a very, very tight fit in the weld-on holder. But I'm not going to do that. Let's take the screw out. So I figured I could take, let's find a measuring instrument. So I figured since the shaft of the indicator holder is 20 millimeter long, I could cut it down quite a bit. So I took a 6 millimeter end mill, and I'm using this to determine the depth of the bore. And well, the bore is quite deep. So the bore is about 35 millimeters deep from the face of from the tool holder. So measuring back, oh sorry, it's 45 millimeters because I can't read the tape measure. It's going back to here approximately, not here. So that's the depth of the bore. I know for a fact that the bore is not finished all the way through. It's relieved in the back here. That's the depth of the bore. If I take 20 millimeters from here, I end up here on this line here, approximately, of course. And that means that I gain about, let's see, 25 millimeters in height, which is almost the height of the dial test indicator holder. So that's significant. So let's go to the surface grinder and cut this off. I'm going to use the punch grinding fixture to abrasive cut off the end of this tool holder. So using dial test indicator to get its run out reasonable true on its outside. So when I grind a little bit of a chamfer on it, it doesn't look like amateur hour. The part is held in a V-block, and the V-block can be slid up and down with a rack and pinion to get its run out true. So we are low here and high here, so I have to drop the V-block down a little bit. Okay, that's within 30 micron already. low, high. So dropping it a little bit more. That's 10 micron. I mean, we're using an abrasive cutoff wheel and grinding a chamfer afterwards, so that went quite well. Now we can spin this chamfer on here. I don't have a certain dimension in mind for the chamfer. I'm just I let my heart guide me. This looks like the perfect chamfer for this operation. I forgot to face grind it, so I have to take this off anyways. Let's get the magnetic V-block out of the way. Nope, I don't know who makes these. The box doesn't have a manufacturer on it. That's a case of good luck finding it, to be honest. Sorry, I don't have a good answer if you want to know where this is from. Also, I haven't seen an adjustable magnetic transfer block in any of the big tooling catalogs. So your guess is as good as mine. The trouble with getting a thread in the tool holder is that it's at least case hardened. I don't have a hard cutting capable thread mill. I don't have a good thread mill at all here. Would have to grind one. So I figured I'm checking the hardness of the cutoff first before I cobble together a game plan. Let's get the hardness right in the center of the material. A little bit to the inside so it's nice and supported. Getting my preloading. Dropping the weights. Now it's actually indenting the material. Once it settles, you have to wait a few seconds to have it really settle. I think in the standard it's like 30 seconds, but that's fine. Then I hit the lever down here and then it shows me the actual hardness, which is 31 Rockwell on the C scale, Rockwell cone, which is not really hard. It's a tough steel, but it's not hard. But I suppose this is case hardened. Let's check it very close to the bore. Just like this. Again, preloading, indenting. Yeah, this is harder. The needle doesn't drop down as far. Waiting for it to settle, that's fine. Reading the hardness. That's 40 Rockwell C. That's still not super hard. It's like a good heat treated and quenched tool steel. Like not 40 Rockwell C is like the upper end for 42 chromoly that has been delivered in QT status. That's quenched and tempered. Checking the outside of the tool holder. Already preloaded it, dropping the weight. Checking something round on the outside is not ideal. There is a correction factor, but I'm not going to bother with it. Let it settle for a few seconds. That's enough seconds. And let's see. Yeah, that's 50, 55, 57, between 56 and 57. So yeah, this is the outside of the tool holder can definitely be considered hardened and will not be cuttable with high-speed steel tooling. Carbide tooling will not have a big problem going through this hardened crust. So, laying out the center line so I can drill and tap the hole on the drill press. I'm holding the tool holder in grinding vise, and I laid it on its side. And I measured the height from the surface plate to the top of this cylindrical portion. Then I subtracted the radius of this diameter, and I built a gauge block stack with that exact height. And then I have a scriber, which is just a piece of tool steel that's flat lapped on the underside and has been ground on top to a needle. That's a very old school way of doing layout to a high degree of precision. If you don't have a good height gauge for that purpose. That's a toolmaker way of doing it. So yeah, there is my layout line. I can pick this up with a spot drill or something and try to drill through the case hardened layer. Okay, I moved the vise with the part held in it back to the drill press. Why are you not using the milling machine? Well, because the milling machine is set up for a longer lasting project and I can't use it currently, so I have to use the drill press for my little side project here. I have a pointy tool in here just so I can pick up my layout lines. This happens to be a deburring cutter, but this won't cut well. This won't drill very well into hardened steel. So I'm going to try a ball end mill first. Let's give this a chance. 1600 RPM. Bleepity bleep, bleep, bleep. Should have left the parallel under the part. Oh, that's annoying at best. Yeah, because drilling into semi-hard steel won't move the part if there is no parallel underneath it. So let's pick this spot up again. Yeah. This will clean up. This will clean up just fine. And if not, okay. The ball end mill worked as usual. Ball end mill is my go-to solution if I have to drill on a manual machine into something hardened. Now I'm changing to a 4.2mm drill. I'm going to slow down to 1000 RPM because I'm not sure how tough this is here. Well, let's find some cutting oil. Ooh. Oh, this smells like trouble. Oh boy. The case hardening might be deeper than I expected. There we go. Yeah, it's still tough steel, but it will be fine. Tapping will absolutely not cause any problems, I'm sure. The problem is the core is soft, but since it's case hardened, not only the outside is hardened, but the inside of the bore, so where I'm drilling through to the inside, guess what? That's also hardened. I have to find a 4.2mm carbide drill. Yep, I have a 4.2mm carbide drill in a very sorry condition, so if I break this off, I won't be overly sad. There we go. That wasn't nerve-wracking at all. But Stefan, won't this hardened layer on the inside be a problem when you tap it? I'm glad you asked, and yes, it will be a problem. I will tap as deep as I can, and then I will take a... Well, I don't have to tap all the way through. I can just make a set screw with a little bit of a step, so it clears the untapped section. So that will be fine. Let's try. I have a red ring tap here. This is made for hardened, well, hardened, for semi-hard steels. Stefan, did you check if... No, I didn't. Well, that's an M4 tap. Well, let's take this one. This is an M5 tap. Somehow, this is way harder than it should be. I'm just drilling and tapping a hole. It's not like content for a 40-minute video. Let's see if I can tap this without creating a disaster. Hey Stefan, don't you normally power tap? Yeah, but my power tapping has some limits. I already ruined a bread dough today, and I don't want to do some broken tap extraction on this tool holder. So I'm a little bit careful. Something is happening, so I'm going to open this chuck and get this out of the... Oh hey, turns out the tapping wasn't a problem at all. Since I only have a cheap benchwise, I have to use this one. Let's unwind the tap here. Turns out this tap didn't have any trouble with the little bit of hardened layer on the inside of the tool holder bore. Hey, that worked way better than it had any right to, apart from the problems I created for myself. So yeah, there is a super short, well-done tool holder. If you look down in there, I bent a little loop-de-loop out of 1mm copper wire, so when I put the set screw in, I'm not pressing with the set screw against the shank, but there is a soft piece of copper in between. So shorten the set screw a little bit, and I can really grunk down on this set screw. And there is my new super short, well-done tool holder for the low profile diode test indicator holder. And compared to the standard 6mm well-done, I'm gaining quite a bit of height. I like this. I like when the tooling that I use is about the same length that my measuring tooling has. So that if there is no huge difference in length means a lot less z-axis movement to get where you want to be. So yeah, that's it. Cutting down tool holder and drilling, tapping a hole. Woohoo! Over at the CNC, because otherwise you will yell at me for not showing it in the machine. And with all that would only be fair. So there we go. Yeah, that's I like that. That's very compact, and I still have a lot of C height above the vise, despite this vise being almost as tall as Abraham Lincoln's hat. I still have, that's about 40 millimeters of distance. So yeah, I'm very happy with. I mean, it was a really simple thing to do, but I'm really happy that I finally did it after over a year. While I've been dealing with the hardened tool holder, I was thinking, well, maybe let's look at some different things and check their hardness. I lined up a few things that might be interesting. Starting in the back is tool steel, unheat treated or annealed O2 tool steel 12842. Then we have P20 plus S, which in the ISO world is 12312, in a QT configuration. That means it's hardened, quenched, and tempered. So it has some strength to it. Then I have a heavy-duty fixture washer, a piece of Toolox 44, which is a heat-treated tool steel, a grinding vise, a piece of A2 tool steel that I flame hardened here in the shop, and I left the heat treat scale on one side and I surface ground the other side, so there is an effect that I want to show you. Box cutter blade, piece of hydraulic rod, piece of D2 tool steel air hardened. This is a drop of a wire EDM machine cutting tool die components, and a piece of high-speed steel. So to be honest, they're already lined up quite in increasing hardness the further you go this direction. But especially the O2 tool steel in the annealed state might be interesting, because sometimes people say, well, I use tool steel. I won't harden it, but it will be stronger and harder than regular steel. So, and to be honest, I said that in the past too. And it's, well, let's see. So let's do some hardness testing here. Let's start with the probably hardest, with the high-speed steel. This is just a Momax Cobalt high-speed steel blank. Hardness testing, the cleanliness of the anvil surface and the cleanliness of the backside of the part are very, very important, because the hardness shown up here is a direct function of how deep the diamond can indent the material. 2 microns of depth change of the diamond is 1 point of hardness up here. So there is a direct correlation between those two things. And if your test subject is not sitting perfectly stable on the anvil of the hardness tester, you get very inconsistent and often wrong readings. So that's why I usually stone the back of the part either with a flat ground stone or on the magic sanding plate. So then we go up with, we raise the part into the diamond and we get our preload, and the needle will stop at 0. You can over travel a little bit, but the preload will stay the same. It's quite the clever technique. Then I can drop the weights by the lever down there, and once it settles out, we'll give it a few seconds, and then we push the lever down and we get a hardness reading. And we get 67 and a little bit, so 67.5 Rockwell C. That's what I would expect of high-speed steel. That's hard. That's really, really hard. If you try to touch this with a file, you will damage the file. The next is the D2 tool steel, also hardened. This is from, well, this is tool and die material. Let's drop the diamond, preload it. This is fairly hard too, but so we end up in this case at 60.5 Rockwell C. So that's D2 tool steel, hardened and tempered. Next one is a fun one, hydraulic rod. This is case hardened and chromed. And it's round, so this is already a pain. I need a V-block. At one point in time I will make me a V-block that's centered under the diamond, but for now this will have to do. So let's get our preload here. There's the preload, dropping the weights. And I know for a fact that the hydraulic rod is fairly hard. That's a combination of the case hardening and the chroming. We get about a little bit under 60 Rockwell C. So this is quite a nice material to make things out of. You just have to be careful because it's far from round. Hydraulic rod tends to be fairly non-round. It tends to be trilobular. So if you measure it with a micrometer at different orientations, it will appear to be round. But if you spin it in a V-block or in a very precise spindle and you put an indicator on it, well, it won't be round. Had to learn that the hard way. So now box cutter blade. This is a fairly... So this is relatively thin, and I would consider this the thinnest piece that you can check with a Rockwell C hardness tester, because the diamond will otherwise put a dent on the back side of the part, and that will falsify your reading. So dropping weights. But box cutter blades are surprisingly hard. Yeah, the weight has settled out. So we end up at 61 Rockwell C. And that's not bad for a mass-produced cheap item like a box cutter blade. Now, cheap grinding wise. I do like cheap grinding vices. They have been very good to me from a performance standpoint, and they last quite a long time because they are have usually a decent heat treat. So this one needs a regrind anyways, because this is the one I use to hold stones when I grind them. There is some severe wear on this one, and I don't mind putting some indentations on the top of it. Okay, it has settled out. That's 58 Rockwell C. As I said, this is it's a very decent heat treat. A file won't touch this. So all these things I would consider hardened. All the things that we have checked now, I would consider hardened steels. Everything that's coming now, apart from the A2, which I will do at last, everything else that I will show you, I consider soft or tough steels. Let's start with the Toolhox 44. This is a commercial heat-treated tool steel. It's great for stuff that needs to be very tough, but you don't want to heat treat. And it even can be welded to a certain degree with some preparation, mostly preheat. And it's called Toolhox 44 for a reason. The 44 is its hardness spec within reason. We get 46 Rockwell C out of this piece. 46 is soft enough so you can drill it with high-speed steel, you can tap it with high-speed steel, and you can kind of bandsaw it too. It's a little bit of pain to work with high-speed steel tooling, but it can be machined. Not a problem with carbide. So let's go down the line. This is the heavy-duty fixture washer. These are heat treated, and I cleaned up a spot up here from the black scaling. Whoop, preload. Some people call these washers hardened. They are not really hardened, but whatever. They are usually a very decent heat treat. So the needle settles out. So this one is 39 Rockwell C, which is far from hardened, but also it's a decent toughness. Next one, P20 plus S 12312, which is, well, it's a tool steel, which comes usually in a pre-heat treated state. It can be used for all sorts of things. I made lathe tool holder blocks out of it in the past because it comes with a nice toughness and a little bit of hardness. It's a fairly good material and machine's beautiful, but it's not really hard. With high-speed steel tools, it's super easy to work with. It comes out at 31 Rockwell C, so not amazing, but also nothing to sneeze at. And the last one is O2 tool steel annealed. This is how you would get it from your steel dealer. And as I said, tool steels without heat treat are kind of useless. Tool steel, soft, let's see. There is a lower limit to the Rockwell C scale where it doesn't make any sense anymore. And this is one of those cases. So let's see what we get. It's settled out. Yeah, 10 Rockwell C. It's kind of useless at this point. This is just soft. Okay, and the last one that I saved is the piece of A2 tool steel. A2 is the air hardening tool steel, so I just torch hardened it. And I surface ground off 20 microns off one side to get rid of the scaling from hardening, and I left the scale on the other side for a reason. In the back side is just sanded on the sanding plate. So first we check on the scale, on the scaling. The heat treat is not brilliant on this, but we should get a result. So we get 56 on the scaling. Let's do a second one. 51. And let's do a third one. That's 55. That's 55. Now we go to the surface ground side where I removed the scale. Let's do three measurements again. That's 61 and a half. That's 63 and a half. Okay. And 63. So there is still some tolerance in my measurements because this is just flame heat treat. But the scale, well, there are two factors at play when you flame harden in an atmosphere. First of all, you have the scaling, which is this oxide layer that's kind of crusty, and also you are decarburizing the outer layer of the steel. So for real hardness, you want to get rid of at least the scaling and maybe even a few microns of the steel. If you do a flame harden, you plan to do a post heat treat anyways. Otherwise, you end up with not very nice parts. So I'm not sure if this experiment is very descriptive, but even the manual of the hardness tester says or tells you when you test your object, the test area should be clean, smooth surface, no big machining marks. In most heat treat, when you have something heat treated, you will usually find a spot where they used emery cloth and they just cleaned off a spot of the scaling and hardness test there. Usually that's in a spot that will be super visible later. So, after watching this, you might rightfully say, but Stefan, you surface ground the half of the workpiece. The heat treater who checks the hardness won't do this. And you are very correct in that case. So let's do what the heat treater would do. He would probably just take the part or a piece of emery cloth and just do this. And clean up a little bit of a spot so it's bright metal. I think you can see the difference between the sanded side over here and the surface ground side over here. So this is now on the sanded side where I just removed the scaling on the sanding plate. And this gives us 62 Rockwell C, which is very comparable to the result I got on the surface ground side. It goes to show even just rubbing off the scaling to bright metal improves the performance of the hardness tester by a lot. This is way closer to the real reading than what we got before on the scale. And also, let's have a file here. Bring the part up to the microphone. This sounds like 60 HRC. This is the noise of a file getting destroyed. One more time. So I hope you enjoyed this little hardness testing side plot and also the tooling modification. I hope you learned something, hope you enjoyed. Thank you all for watching, thanks for the support, and I'll be back.